Hey and welcome back. This is the third video of this tutorial series. In this video, I'll show you guys how to derive the equations that I promised I will derive earlier. So let's begin with the input terminals. So here you have, for example, the common mode at both ends, which is reasonable. But these are buffer amplifiers. So what you have is the same voltage at this point at the input. So if you have VCM at this point, you have VCM at this point. So same over here, you have VCM at this point also. So there's no change in potential, there's no current flowing. So it is also VCM at this node right here and VCM at this node right here. The key point here is that there's no current, so there's no change in potential. So what you have is the same potential here, same potential here, here, here. Okay? So now I have a voltage, I have the resistant value, these resistant value. I can start writing the currents flowing through this resistor, flowing through this resistor, and through this circuit. The reason there's current flowing to this point, from this point to this point, from this point to this point, is because this is a ground here, and this is also 0 volt because it's the op amp rule you have to remember. So if this is 0 volt and this is VCM, some finite number, then you have a current flowing this way, and this current here is equal to VCM over RA. And this is the same magnitude, I equals to VCM over RA. So what does that mean? That means that we can come up with the easier equivalent circuit seen below here. So I have modeled everything here using just a common a voltage source VCM divided by this is the RA over 2 and then this is the 0 volt here, no, right here. So this is the same thing right here because the total current flowing through RF is what? This current plus this current, because there has to be current flowing out, right? Because these two currents are flowing into the node, so this current flowing out has to be IF equal to VCM divided by RA over 2, which is 2 VCM over RA. So that is effectively what this equivalent circuit does. It basically describes this this phenomena right here. So you have a current flowing this way that is 2 VCM over RA, and let's call this ICM. Let me write that again, that's kind of messy. So different color, yeah. So ICM at this point, ICM is equal to 2 VCM over RA. And guess what? RF is equal to what? 0 minus V out. This is V out. So you have minus V out over RF. Whoops, 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 whoops. This is IF is equal to minus V out over RF. This is basically KCL. So what do we have next? Okay, we use this formula here. So yeah, again, KCL. So let me start over here. KCL at this node right here. So you have current ICM is equal to IF. So I start writing in terms of voltages, which is 2 VCM over RA is equal to minus V out over RF. And then I'll write this in terms of V out. So V out is equal to, after rearranging things, you have 2 RF over RA times VCM. Now I want to derive a final equation that relates the common mode voltage to the equivalent resistant I talked about earlier. Now let me see if I can show you that the picture again. So remember earlier I was talking about this equivalent resistance. I want to derive that equation, how I came up with this model right here. So we need another equation, okay? So at this point, it's V out, right? So I have my VCM. Okay, yeah. Before we do that, I want to mention this insight. So you have from 0 volt flowing. So the current is flowing this way. You assume current flowing this way. So you're assuming your V out will be minus. So it'll be negative. It's less potential than 0 volt. That means that means this is flowing this way, right? Because VCM is higher than over here. VCM is higher than 0 volt. It's flowing this way. So over here, VCM has to be higher than a negative voltage, right? So this current right here we call IP for parasitic. It's flowing this way. Okay. So we're saying V common mode is higher than V out. So we can do this. So we can write V common mode is equal to V out plus IP times R right leg. Does this make sense? So if we assume that VCM is higher than V out, then V out plus some positive term here will equals to a higher value VCM. So right now we have two equations, right? This is one equation, two equation. So I'll substitute my V out here into this part right here. So I have my VCM is equal to minus 2RF over RA times VCM plus IP IP times R right leg. So at this point we can reduce this down by divide everything by VCM basically. So you have 1 is equal to minus 2RF over RA plus IP R right leg over VCM, and then you simplify this further and you get VCM is equal to R right leg over 2RF over RA plus 1, and then this is multiplied by IP, and voila, this part right here is the R equivalent or R effective that I mentioned earlier. Now you see. So what happens is that when you reduce, given a constant R right leg, this is the electro resistant. When you increase RF to RF RA ratio, then you will lower the overall VCM, because VCM can only drive a finite IP into the electrode here. So that's one of the ways you can like drive down VCM. So that will improve your common mode rejection ratio. Okay. So that is how you derive the formula. In the next video, I'll talk about more of the practical areas of using the circuit, such as including additional components such as a guard output, where you can plug into your shield cable or your shield, and then that's actually helps with the decrease the electromagnetic interference. Anyways, thanks for watching. See you in the next video.